My name is Dan Baker. This is my first time presenting at GRCon, second year attending. Some of these slides were contributed by my colleague Brian Avenell, who spoke last year at GRCon in Henderson on receiver architectures. All right, that's the bad spot right there. So I'm going to stand over here. So apparently it's hardware day today at GRCon because we're going from one hardware talk to the next, and so I apologize for that. Hopefully I can hold your attention for the next 25 to 30 minutes. I tried to keep the slide deck somewhat short so there'd be time for questions. We're going to talk all about synchronization, specifically at the RF side, the local oscillator side. I am not in marketing. I am a design engineer, been at National Instruments for a very long time, working on instrumentation and software-defined radios for quite a while now. And I'd be happy to take questions after this for anybody who wants to dive in deeper for stuff that we're not going to get a chance to talk about. But let's start with some descriptions of some existing RF systems and try to frame the problem a little bit here. So one of the things that National Instruments Edis Research gets involved with a lot is building these sort of larger systems where there's a lot of channels that all need to be synchronized well together, data streaming at very high rates, real-time processing, end-to-end links, et cetera. And one example of that is this massive MIMO system that we put together many years ago as people were trying to research what massive MIMO could be. At that point in time, it was just theoretical. And running MATLAB sims is one thing, but if you can actually do an end-to-end link and prove that it works, that's something else entirely different. And so we were able to use existing X310s. Here you see 4 racks that have 128 channels of X310s. But it's not just record and playback. This is real-time streaming through all those chassis that you see at the bottom and is actually doing a real-time end-to-end link. And this system was actually used for prototyping full-dimensional MIMO or spatial multiplexing. And so in this case, you might say, well, what are all those antennas for? Why did it need that many? And what they were trying to do in this case, these were researchers at a particular university, and there are versions of this at universities around the world who have been publishing papers for the last several years based on this particular system. What they were trying to do here is communicate unique messages to multiple users at the same time and at the same frequency. So they weren't multiplexing in the time domain, they weren't multiplexing in the frequency domain, they were multiplexing spatially. And so there's actually a cool YouTube video you can watch where they have this system in one room, and in the next room they have some microphone stands set up to represent people, and they have an omnidirectional antenna on each of those microphone stands. And at the same time and on the same frequencies, each of those antennas was receiving a unique stream of data. Right? So that's spatial multiplexing. And the way that works is basically through some clever math, you can transmit similar versions of the same signal out all of these 128 channels and create a beam, right? Beamforming, you guys have heard this before. And beamforming is a key technology that will be used in millimeter wave 5GNR. And the idea there is they want to form these like pencil beams, right? These super narrow beams to be able to pinpoint all of your RF energy in one particular direction. But to do that, these RF channels have to be well aligned, both when you're transmitting as well as when you're receiving. In this particular example, actually the way that the local oscillators were aligned was using ref clock sharing. And later I'll show some measurements, and you can see it's not actually the most precise way to do it, but it was plenty good enough for this application. Another application we can look to, this one's actually over in our NI Edis booth over there. This is a direction finding example. Here's the link to the knowledge base on edis.com. And here you have 4 antennas, right? 4 omnidirectional antennas that are all near each other, hooked up to 4 channels of some twin RXs that are in a X310. And those twin RXs, in this case, are sharing the local oscillators. And so you can see what would happen here if you're using a system like this to attempt to determine the angle of arrival of some incoming signal. Well, if that signal is coming in from your right, then the antenna that's on your right is going to detect that RF energy first before the antenna that's on your left will detect it, right? So you can get a sense of, oh, okay, the wavefront's coming through, and then tuck, 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 it hits all the antennas, one right after the next. And so this example uses an algorithm called music that basically looks at the time of arrival of when the signal hit each of the antennas to figure out, oh, the angle of arrival of when that was coming from. And okay, that's pretty straightforward. It kind of makes sense in our heads. But you can imagine there is if your RF signals are not really well aligned, it'll throw the whole thing off, right? Because what if one of the receivers is a nanosecond out of time alignment with the rest of the receivers? That'll totally throw off the algorithm because you think that the signal arrived earlier and it actually arrived later because these receivers are not well aligned. And so having LO synchronization in these types of applications is critical. And what you might hope for is that right out of the box, all of these RF channels are just perfectly aligned. You hook up your antennas, you run the example, done. But in reality, you generally need to do some type of a calibration step. And you see this with sort of large direction-finding systems where they might have a calibration source that is transmitted as sort of a equal distance from all receiving antennas, and then you use that to align the times digitally. And if we have time at the end, I'll talk about some of the techniques that are used for doing digital time alignment. In this case, the reason that the LOs are actually shared is to get more coherent phase noise between each of the receivers. And so that gives you more precision as to the angle of arrival. So you can imagine if these receivers are well aligned and they have correlated phase noise, you can get a pretty good notion as to where the signal is coming from. If there's uncorrelated phase noise between the receivers, then maybe you don't get quite so much precision as to where that is coming from, right? So that's kind of the main theory behind it there. Third example that I thought was a useful analogy, okay, this isn't a traditional RF receiver, but just think about a nice oscilloscope from Tektronix. You buy this thing, you spend a lot of money for it, you get it out of the box, you hook up the probes, you go to probe your circuit, you look at what's on the screen, and you see that, oh, here's the clock going to my flip-flop, here's the data going to my flip-flop, or I probe the same signal. You expect them to be aligned, right? You don't expect that every time you boot your oscilloscope, there's some misalignment between the channels of some unknown amount that you have to then correct for. You just expect that out of the box it's aligned. But the reality is actually if you're a high-end signal integrity person, then you actually probably own one of these D-SKU kits, which you can also buy from Tektronix. Not nearly as popular, but you can use these to probe the exact same signal with two of your probes and find out that, oh, these two channels are off by 12 picoseconds because there might be some mismatch in the probes or whatnot. And so you use a D-SKU kit like that, and then you digitally D-SKU those channels to get them just perfectly aligned before you do your DDR4 timing measurements, right? So here, and again, an example of a situation where there's some amount of out-of-the-box alignment that you just sort of expect. But if you want the ultimate precision, you have to put a little bit more work into it. All right, so what does it actually mean to be synchronized? I work for National Instruments. It's a big company. We have a lot of different products that we make. And so I'll get pulled into these meetings sometimes with folks from other departments. And it'll be a synchronization meeting. And so, okay, I'm one of the guys who knows things about synchronizations. Great, I get pulled into the meeting. And we're 20 minutes into the meeting, and we're like, disagreeing on things, right? And I realize it's because, for me, synchronization is a picosecond, or maybe even into the femtosecond range. And for this guy, for the application he's working on for, machine condition monitoring, whatever, like a millisecond is pretty good, and a microsecond's awesome. And so we need to have some understanding of sort of what level of synchronization is required for the application you're trying to build. So in this talk, I'm going to get a little bit into the details of things that we bake into our products, but also I try to get into the things that are useful as you're building systems out of products such as ours. Back in the 1800s, there was no notion of synchronization. Early 1800s, every town set their clock to, it was noon when the sun was overhead, right? The sun's straight up in the sky, that's noon. And there wasn't a need to have synchronized clocks between cities because, well, if it took you 2 hours on horseback to get from one city to the next, you didn't really know if the two towns' clocks were out of phase by 15 minutes, like nobody knew it. And then the trains came along. And so with a network between cities, you now had to have coordinated time of some kind. There's a link to an article at the bottom of the page. 1840, Greenwich Mean Time was introduced. And so the idea being that the clocks on the towers and the train stations would be synchronized to some degree so that you could have matching timetables of understanding when the train was coming and going and not have quite so much chaos on that early network. So what does it mean to be synchronized? Maybe 1 minute is good enough for train stations. Maybe 1 second or better when I'm trying to click that button to check in for my Southwest flight, right? I got B12 coming here. I was pretty disappointed, to be honest. I'd like to get into the A's if I can. I thought I was right on it, but I guess it didn't work. A millisecond is detectable in audio. So think about it. You go to one of these huge stadium events, and they've got the big speakers in the front, right? But then as you go further back in the stadium, there's a second rank of speakers and then a third rank of speakers. And they delay the electrical signals going to the second and third ranks such that the audio coming out of the speakers in the back of the room lines up with the wavefront that was coming from the front of the stadium. And if you get that off by more than a millisecond, you'll hear the double click, right? You'll hear the double beat of that. But if it's within a millisecond, you probably won't ever notice, right? And you get to these precise control systems, robotic surgeries. You get to a point where a microsecond is really, really needed. And then you start to look at, well, the baseband in my large RF system, maybe a nanosecond's good enough. And then, well, I want to do some really precise pencil beam forming. Okay, you better be down to the picosecond, right? And so the point of this is, well, what's really required for your application? Because if you are trying to align everything down to the picosecond, you can do it, but it's expensive, it takes a lot of time, it's extremely temperature unstable, you breathe on it, right, and the thing shifts. And you go for coffee, you come back, and it's all shifted out of phase again. And so you don't want to go for too little and say, oh, a millisecond's probably good enough, and then you end up with a beam forming that's this wide. But if you really need that precision, then it's going to take some extra time and effort, but it is possible. All right, really basic diagrams, sine waves. Turns out sine waves are very hard to draw in PowerPoint. I did this in the airport in another country the week before last, and I was not happy with the results, but it was close enough. Imagine here, let's see, what's a good analogy? Let's say we have two usurps, and they're each generating 50 megahertz signals. And you take those 50 megahertz signals and you hook them into that tectronic scope I showed earlier, and you trigger the scope on the blue signal, and then you look at the green signal to see is it lined up with the blue signal. Okay, that's the picture. And if those usurps were not attempted to be synchronized at all, then the green signal would just be all over the place, right? It's not phase locked, it's not frequency locked, it's not nothing. But if they were fully aligned, this is what you would see. And you could zoom in on that rising edge just as far as you can possibly go on the scope, and you're like, man, these things are just perfectly aligned. So this is kind of the definition of fully aligned signals. More than often, the best you can really hope for is something like this, where you have a fixed offset. So I've got a synchronized system. I don't actually know what the difference is between my two RF signals, but it's fixed, it's consistent, it stays there over time in temperature. I can measure it, and then I can adjust for it digitally. And this is really kind of the best you can hope for in most scenarios, and then you can correct for it digitally. If you're not careful, you can end up in a situation like this, where you have aligned signals and they're phase locked, but they're drifting over time somehow. And what is causing that drift? And I'm going to show you in a couple of slides where that's coming from. You can also end up in a scenario like this, where you have short-term phase incoherence. So you have uncorrelated jitter between your RF signals on multiple channels. What causes this, and does it matter? So we'll talk about that in a few slides. And then really the worst case scenario, and it's pretty easy to get into this scenario when you're designing a product, is where you have run-to-run mismatch, right? You stop your radio flow graph, you get some coffee, you come back, you run it again, and whoa, that offset changed. What happened? What did it move, right? Or you shut down for the night, you turn it back on, you had done all this work to get your system nicely calibrated, and it's different now. Why is it different now? And a lot of this is actually due to baseband. And following this talk, my colleague Daniel Jepson is going to talk about baseband synchronization. Turns out there are a bunch of ways to mess this up and make this occur, and there's really a lot of things you have to do to make this not occur. And a lot of it is on us at National Instruments to make sure that this doesn't end up in our products, and anybody who's designing their own software-defined radio. But some of it is actually important at the system level, too. So that'll be the next talk after the break. So where do the problems come from? Here's a receiver architecture similar to the one that was presented earlier. Your RF signal comes in on the right. No, I did not put the bandpass filter before the LNA, just like he showed. You have a low noise amplifier, step attenuators, filter banks. either an IQ demod or a single stage or multi-stage down conversion, more filters, an ADC. And so this local oscillator, this is a key piece of the equation here. The LO, it's local, right? It's on your device. It's in the name. It's local. It's not a global oscillator. It's a local oscillator. And so it has its own phase, and that phase is maybe just random if you haven't made any attempts to synchronize it in any way, shape, or form. Even if you have, it's going to be relative to that 10 megahertz reference that's coming in on the left side. The ADC can have its own phase, and maybe if you're using a JESD204B ADC, you have subclass 1 synchronization, and so you think, great, this is going to solve it for me. But that's actually kind of tricky to get that to work, especially at those higher rates. And then that data comes into the FPGA where you have a DDC. What's inside the DDC? An oscillator, the NCO or a Cordic oscillator. That's going to have a phase. Oh, decimation filters? Oh, those have phases because they have counters. They're counting, right? And so sort of everything along the way, every time you have a divider, a clock divider, an oscillator of any kind, it can have its own phase. And if you haven't taken sort of great lengths to make sure all those phases get reset properly to the right spot relative to some known epoch time in your system, then you're going to end up with all sorts of rough things that occur. So it does come from a lot of places. So what can we do about it? First, when we're designing devices, we can try to be really careful. Like that 10 megahertz buffer, this guy in the top left, that first buffer that receives at 10 megahertz, that's actually a really critical part right there. Extremely critical, because you have something in your system that's distributing, say, a 10 megahertz reference to all those devices. That big massive MIMO system, we were using octoclocks, 128 channels of this thing, right? And so you've got to distribute that to all of them, but then each of these buffers receives that 10 megahertz. What if that buffer has significant temperature skew, right? Its propagation delay varies over temperature. That'd kind of be a big deal, right? So one of the things that we can do is try to select very specific components that have low skew over temperature, very specific components like PLLs that can be reset properly. And so we try to bake that into the devices that we're designing now. The converter clocking and synchronization, the way that you distribute, say, PPS, or if you're using White Rabbit or GPS, that's important. That'll be in the next presentation. But local oscillators is what I'm going to focus on for the rest of this presentation. So here's the same drawing that we had earlier. So that local oscillator, somehow we have to give it a global notion, right? We have to kind of make it a global oscillator if we can. So there's 3 different ways you can do that. One is that you can share a common reference clock to all the receiver channels or transmitter channels in your device, and then have some common way to reset them all such that all their counters are reset to exactly the same phase. That's kind of the nicest and easiest way to do it because you don't end up with any extra cables at that point in time. You have your reference clock and PPS cables, but you don't have to cable around local oscillators. So it's a little bit easier to do it that way. The next way is daisy chaining, where you actually are distributing the local oscillator from the first device to the second to the third. And then the third way is star distribution. So let's talk about all 3 of those. Reference clock sharing, as I said, was using that massive MIMO system. There's a few different ways you can get your reference clock, either from a 10 megahertz distribution source like an octoclock, GPS, DO, White Rabbit. There's other ways that you can do it as well. You have to have pretty specific PLLs here. You've got to choose local oscillator generators that are capable of doing this. Gene highlighted in the last presentation about some of the new analog devices parts that this is a big feature, right, in their new parts, because it's pretty tricky to get this right. So what happens when you actually try this out? These are measurements that I took a while ago in my lab on a couple of NI instruments, not actually on X310s, but I took the same measurement on X310s, and it was pretty similar. And what you see here is, I'll kind of point out some of the axes, because I'm sure it's hard to see in the back of the room. This is phase drift on the y-axis here, and this is at 3.6 gigahertz center frequency. And this is time on the x-axis. This is over about an hour and a half, and I've seen about 5.5 degrees of phase drift. And then you also see, like, kind of vertically, it looks pretty noisy, right? That noise. So that sort of 1 degrees-ish of noise, that's uncorrelated phase noise between the devices. That's that uncorrelated jitter. And then that sort of 5.5 degrees of drift that you see, this is over about 10 or 20 degrees Celsius of temperature change. And that's kind of a lot. It may not matter for your application. Maybe that's good enough. It's going to take that narrow beam and it's going to make it a little bit wider, right? And a little bit jittery. But maybe that's perfectly fine for the application that you care about. And let me go back up one here. You see that each of these devices has their own PLL. And so each PLL has its own phase noise profile, right? They're going to be uncorrelated to each other. So we've aligned the phases of these local oscillators. We haven't done anything to make them coherent to each other in this case. But it is pretty nice because you only have to distribute these two signals. Part of the reason that drift occurs is because you're distributing a 10 megahertz reference clock, and then that's effectively getting multiplied up to 3.6 gigahertz, right? And so you remember how I said that first buffer is super important? So the 10 megahertz reference clock has some slope to it, and of course it's going to have a little bit of noise, voltage noise on it, because it's a signal that's going to have some voltage noise. Well, when the slope of that goes through the threshold of that input buffer, that voltage noise is going to get translated to time noise, right? And that time noise is basically where your drift is going to come through. And there's some other slides from Brian Avenell that kind of walk through all of it. In the end, you can make some assumptions and do some maths, and you come up with, oh yeah, this is like tens of degrees at 6 gigahertz. So how else can we do this? Another approach is daisy chaining. So what you see in this picture here is the first device, the first transceiver, is generating its own local oscillator and then exporting that to the second device that imports it, who then exports it to the third device, who imports it and exports it. You go, fantastic. I just need one extra cable between devices here, and now I have correlated phase noise, right? Oh, that's great. Well, it does get a little bit harder the further you go down the chain, because you now end up having quite a bit of cable between the first device and the last device. And that cable has generally, unless you buy super expensive cable or they're really, really, really short cables, there's a property called the Teflon knee problem, where sort of near room temperature, the properties of Teflon sort of change dramatically. There's a knee in the curve. And if you're kind of near that knee, it doesn't take too much of a temperature change before you actually get somewhat significant propagation delay. And so basically, as you go down the line here, your phase noise becomes less and less correlated, and your drift becomes sort of worse and worse. So the first few devices in the chain are all right, but as you have a ton of devices daisy chain like this, it's going to get sort of worse and worse as you head down the chain. So this is good for a small number of channels like this 4-channel direction finding application that we have over in the booth. And this is typically what is done in high-end instrumentation. So I took some measurements. This is just for 2 devices that were daisy chained together. And this is at the same 3.6 gigahertz, same axes. So now you're getting about 1.5 degrees of drift over, again, a 10 to 20 degrees Celsius change, and sort of 0.1s of degrees of noise of short-term incoherency. So you see this picture is way more precise than the previous one I showed, right? It's significantly better. But this is just for one stage in the daisy chain. So if you do a third, a fourth, a fifth, a sixth, a seventh, an eighth, a 10th, a 100th, it gets worse and worse and worse as you go. So what do we do about that? There is one more thing you can do to make it a little bit better. Oh, sorry, forgot this slide. And so this is a graph that shows a little bit of the properties of those delayed cables. And sort of the longer you get down the chain and the higher frequency you're at, sort of the worse it gets. So one more approach you can take is star distribution. And this is something that my colleague Brian Avenell built into the new N320 and N321 products that we make at National Instruments. In fact, all these SMAs that you see across the top up here on the top right, it's a whole ton of SMAs in the N321. And what those are is a big splitter network for distributing LOs in a really cool way. Turns out this works extremely well. So the first device in the chain exports its local oscillator, which then goes through a splitter network, which goes back to itself as well as to other devices in the chain. And then you can daisy chain these groups together. So you end up with somewhat of a hybrid network of mostly star distributed and somewhat daisy chained. And this is really useful for large systems where you need sort of precise alignment and nice correlated phase noise over a whole lot of channels. I'll keep talking louder to see if I can outpace the guys over there in the demo room.
We're technically supposed to be in break now.
All right.
20 minutes behind before you started.
I understand. I'm known for messing things up. So I will try to get done here in 7 minutes. Maybe 6.
Yeah, 15.
All right. So what do you do here? So you take some measurements, and these are measurements that were taken on the N320 and N321. This is actually worst case measurements, worse than the ones I showed on the previous slides. This is over 45 degrees C of variability in temperature, and it was done at 6 gigahertz instead of 3.6. And here you see it's actually about just under 1 degrees of phase drift. So this scale is actually a lower scale. This is 1.2 degrees on the y-axis here. So under 1 degree of phase drift over 45 degrees C temperature. So that's really incredible. Like that's pretty tight. That's going to keep that pencil beam, right, really nice and well defined. It's going to keep your direction finding algorithm pointed in the nice direction there. And the short-term incoherency is pretty low. It's extremely low. So there's a knowledge base on edis.com. I'd encourage you to go there, read it. It's got the UHD example code. The direction finding application has the GNU radio code on it as well. And what you can see in this N321 diagram is that each of the receivers and transmitters has an associated LO distribution section where you can export the internal LO, you can import an external LO, and there's a 1-to-4 splitter and an amplifier. And this allows you to do things like put an N320 and an N321 together to build a very nice, tightly coupled 4x4 system, or put several of those together to build an 8x8 system, or put several of those together to build a 32x32 system, or put several of those together to build a 128x128 system, right? And so this is in my opinion, it's a pretty cool advancement in that mid-range SDR of a feature that just hasn't been there on existing mid-range SDRs. And I think this will unlock some new application areas, and I'm really excited to see what people do with it. Again, it's if you need that level of precision in how you're aligning your LOs for these large systems, but it'll give you the opportunity to try that out. So the knowledge base is on edis.com. I'd recommend hitting that up. I'm going to probably skip this digital compensation section. I really didn't have, I knew I wasn't going to have time for it. All of it to say is there are a few different ways that you can compensate for delays when you build your system out and you go, okay, I measured it, and sure enough, I'm off by 15 picoseconds, or I'm off by 1.5 degrees at a particular frequency. What do you do about it? You can adjust for that in the phase of your NCOs. You can do a phase rotation with an IQ multiplication. And if you need to do a physical time delay, not a phase delay, but a time delay, of course you can use single steps of a clock inside the FPGA as an example, but that's not very precise. Those are coarse steps. And the other cool way to do this is using an all-pass FIR filter, right, where you basically have a fractional group delay on an all-pass FIR filter. So when you take that continuous time, right, an all-pass filter in the frequency domain is going to be a sync response in the time domain. And so if you have a continuous time sync response and you want to sample that to create a discrete time sync response to make FIR taps out of it, you don't have to center where you sample those points. You could move those points ever so slightly to the right or to the left, and you can get a fractional group delay out of it. And if that made sense to you, that means you probably already know how to do it. If it didn't, I'm sorry. I decided there wasn't going to be enough time to fully cover it in there. But if you want to talk about that, come find me afterwards. So to try to make up time for our break, I'm going to end here. All of this to say, there's a lot of things to take into consideration when you're building a system like this. And I showed the LO aspects of it, but none of this makes any difference if your baseband's jumping around. And so Daniel Jepson will talk about that in the session after the break. Hopefully you can put the two of them together and they'll be useful. We'll continue the day of hardware here at GRCon. And the one thing I want to leave you with is it's important to understand the needs of your system, not over-design, not under-design. I think you have a lot of tools at your disposal when it comes to existing hardware and what you can build system-wise. We'd love to help. Feel free to come chat with me over the break. or any other time at the conference, and I will take questions if you have any, but I bet people are tired of sitting.
Thank you very much, Dan.
Thanks.